Hello dear students. So this is our 14th lecture on this tensors, and today's lecture is okay. So in our previous lecture we have already discussed about that. So the different transformation rules, or how we can write this contravariant and covariant vector. So in some of our previous lectures we have discussed these things. Now today's lecture जो आज का हमारा topic है, that's about if you talk about the अगर हम derivative लेंगे, if you take the derivative of a tensor, right? So in physics, we have so many expressions, like we have so many quantities, like if you talk about the velocity. So like we are writing that if I have that velocity, so velocity we are writing that it is basically a derivative of that position vector. Or you talk about the acceleration or that force, that's m dv by dt, right? So these are basically you are taking now. If you write these quantities vector in tensorial notation, right? So that means you can take their derivative of something that basically gives us like velocity or force. Or if you talk about some Maxwell equations, you can also write them in this tensorial notation, or you can take the derivative of those quantities. And this is our today's lecture, right? So that means if you talk about that, अगर हम for example किसी quantity का हम derivative लेते हैं, right? Like we have this position vector, or if you talk about that velocity, right? So that basically gives us another tensor, right? So that means the derivative of a tensor that gives us another tensor, right? Now our question is that if we make this transformation, अगर हम for example derivative किसी tensor का लेंगे, so after transformation, after taking the derivative, whether that rank of that tensor remains same or not. So we need to check that, right? So I will give one simple example. So if you talk about now in three-dimensional Euclidean spaces, so if you talk about in 3D, Euclidean space. So how we can write that? So we can write that this coordinate transformation will be like this one. So we are writing that x prime alpha, right? So that is equal to so we can write that partial x prime alpha. Okay. So this is very clear. Again, because you can rewrite this as so this is very much clear because so you just have a look on this expression. So this simply when you this alpha prime will be equal to beta. So this is the same that x prime alpha equal to beta. So that means if I have some tensor of rank some alpha, so after transforming, we are basically getting same rank, same tensor, right? We are getting some another tensor but of same rank, right? So that is basically you are getting this one. So you with the help of this transformation matrix, you are basically transforming it from some alpha prime to some beta, right? Okay. Now, so this is basically how these coordinates transform. So if you talk about the velocity transformation, so that means if you take the second derivative of that. So let us write now. So if you talk about the velocity, so this is basically for coordinate transformation, and similarly you can talk about for velocity transformation also. So for velocity transformation, so we can write that. So okay, so that will be equal to okay. So this is very clear. So there's nothing, right? Simply I take the derivative of this thing, right? So d by dt of this x prime alpha. So this is our left hand side, and on our right hand side we have this. We have two quantities. So you can use that product rule and solve this. So you can derive this as So so you just check. So अगर हम इसको देखेंगे तो मैंने यहाँ पे क्या किया? So this is simply that. So our left hand side is same. Now our right hand side is you are taking this, you are this differentiating it. So using product rule. So first you differentiate this second term and then differentiate the first term. So you are basically getting here two terms. So that is basically this, right? So this is what we have. Okay. So if you remember that, so this is our that. So you can let me rewrite this term. So because this is our that second derivative, I can say, right? So I can rewrite my second term. So this will be equal to that. This can be written as, so we can write that d. Oh, okay. So first let me write it this way. So I can write it as. So this is the. I can write that partial two. So you just check if it is right. तो यहाँ पे मैंने क्या किया? तो let's have a look on the first term. तो ये जो हमारी term है, तो यहाँ पे मैंने क्या किया? I basically multiplied that partial x prime delta of delta x is same thing and dy dt is same, right? So what we have done, and rest is same. Okay. So I basically modified it this way, right? So this is basically, if you remember that, or you can put it this way. Okay, so let me write. So this is basically the derivative of that coordinate. So that simply gives us the velocity, right? So this is our that v prime alpha. So that's equal to. Okay, so let me revise now. So what I already told you, if you remember that, अगर हम देखेंगे, for example, if I make coordinate transformation, I am taking the derivative of some tensor. तो मैं एक टेंसर का डेरिवेटिव लेता हूँ, तो that should give me some another tensor but of same rank. Rank remains the same, right? So what we have done, okay, so this was clear up to this point. So यहाँ तक ये ठीक था, because this was our tensor of rank some alpha. So this again the tensor of rank alpha, because or beta with some transformation matrix, right? So by this transformation rule, when we have a look, when we are talking about this velocity transformation. So in velocity transformation, we are getting the two terms. So first term is this one, and this is our second term. तो जो हमारी फर्स्ट टर्म है, तो यहाँ पे जो हमारा, if we have this tensor of rank 1, right? So this again the first term has same rank, but we are getting some new tensor. Or if you talk about some vector, if you take the derivative by this transforming, you are getting another vector but of same order, but same rank, I can say that. So this is, so first term preserves our that transformation property, because transformation property tells us that the rank remains the same when you make the transformation from some primer to some unprimed system, right? So this is very clear for first term. तो एक first term के लिए clear है. Now if you have a look on our second term, so we have the second derivative, so we can have tensor doesn't remain the same. So that means the second term, it basically violates our transformation laws, right? So that means we can say that if, so the condition is valid for the first term, because first term is basically, it preserves for a tensor to be a first order. Suppose this is our tensor of rank alpha of first order. So this first term tells us that the tensor, the tensor of this, the rank of this tensor, remains the same of first order, I mean to say, right? So that this, it preserves our transformation property. It preserves. Now if we have a look on our second term, तो अगर हम second term की बात करेंगे, जो हमारी सेकंड टर्म है, so we can have these derivatives of this derivatives of new coordinates with respect to the old coordinate, right? And if this term is non-zero, अगर ये term non-zero बन जाए, अगर ये zero होगी then it's okay because it preserves our transformation properties, right? Now if this term is non-zero, right? So I will so if the second term is non-zero, if so what will happen? So so that means if our second term will be non-zero, जो हमारी second this double derivative है, second derivative है, if this will be non-zero, it spoils our coordinate transformation, right? So this spoils our coordinate transformation. तो ये coordinate transformation को spoil करता है because coordinate transformation says that it should remain invariant. We should have this covariance relation. So we should have the covariance property. So it remains invariant. Whatever quantity we'll take that coordinate transformation, velocity or acceleration or some new things, some new quantities. So they should remain invariant. The rank remains the same. So hardly matters if you go from some one system to some another system, from some Cartesian to spherical coordinates if you talk about coordinate transformation. So rank should remain same. So that means if this second term is non-zero, so it basically it spoils our that coordinate transformation, right? So you can say that if you talk about now, so we have this orthogonal Galilean transformation. So if you talk about this orthogonal Galilean transformation, suppose we have some system where rotating it through some angle. So if you talk about the rotation of a vector, if you remember that in one of my lectures, so we can generalize that if we have some vector in some two-dimensional space, if we have some motion in two-dimensional space, and if you want to move that vector, right? So if you move the vector, so you can write the transformation laws for that, right? So that means if you talk about now in that, so if you talk about in this orthogonal Galilean transformation, so we know that our x prime will be equal to that is some x cos theta plus y sin of. So if you talk about along x only, so that means that partial x prime by partial x will be equal to that's cos theta, right? So that means here, or so this is basically Galilean transformation. Or if you talk about that in Lorentz transformation, Lorentz, we have that x prime will be equal to some x minus v of t. Okay. Okay. So that means in this case, if you talk about that, if theta remains constant, so if there is no theta, if theta and r remains constant, so that means in that case, our that second term in our derivative, so this second term, so this will be zero in that case, right? So that means I can conclude here because for if you talk about for this, if you talk about in that orthogonal Galilean transformation or if you talk about that Lorentz transformation equations, right? So we can say that they preserve this coordinate transformation, right? So both these, if you talk about this orthogonal Galilean transformation, or if you talk about that this Lorentz transformation, so they preserve that coordinate transformation, right? Now, so we can say that, so we can write that second term should be in that case will be zero. So so we can have that v prime of alpha will be equal to, so that will be equal to partial x prime alpha for this orthogonal Galilean transformation and that Lorentz this transformation. So they preserve this coordinate transformation. So there is no problem in these two systems. But there is a problem, or if you talk about now, if you talk now there is a problem. It poses a big problem when we talk about the general theory of relativity, right? So when we talk about this, or if you talk about the pseudo-Riemannian geometry, right? So in general relativity, so second term is non-zero in that case, right? So we can say that, or if you talk about that in this special theory of relativity, if you talk about the space-time transformation here, right? So we can write that if you talk about that, so in space-time transformation. So what this coordinate differential is, so we can write this the coordinate differential of x prime mu. So that's equal to, so we can write this as, okay, or we can write this as, okay. So this is what I did here. So I'm basically taking this. If you remember that now, it is basically that proper time. So because if you talk about that in special theory of relativity, so you're saying that, so you're writing you're writing that you're taking the transformation with respect to, you're taking the derivative with respect to the proper time, because proper time, as I already told you, if you remember that, so it is that time which remains same for all the frames of reference. It is independent of the it is independent on the frame of the reference. So ये हर किसी के लिए same रहता है. That's basically called a proper time. And another way I have improper time. Suppose I'm staying here, so my time, what I'm calculating on my watch, that's improper time, because this time will be different for someone which is traveling in some space, right? So this now, it is again that time derivative, but it is that proper time which remains the same irrespective of the frame of reference. Okay. And similarly, we can rewrite this term as, so just like you can rewrite this as that partial x prime mu plus. Okay, so this is same thing. So यहाँ पे मेरा, so I am repeating that. So यहाँ पे मैं I talk about the, if you talk about the space-time transformation, right? So this is basically our coordinate differential. So हम देखते हैं कि coordinate differential how it gets transformed if you transform it from some frame, from some primary frame to some unprimary frame. So this is following the same procedure, and I'm again getting here the second order derivative, right? So this is another example where you can find that second order derivative will be zero or non-zero. So we need to take which case we are considering this time. Like agar हम, for example, if you talk about that orthogonal, that Galilean transformation, right? तो उसके लिए, or if you talk about that Lorentz transformation equation, so in that case, so our, that second order derivative will vanish, right? So there is no problem. So that means those two laws, those two transformation laws, they preserve our coordinate transformation. But if you talk about that general theory of relativity, or if you talk about that in space-time transformation, you can say that in coordinate differentials we have the second term also, second derivative, right? So that means this is our that dx prime u upon dt. Or you can write this as, so this will be equal to v prime nu equal to, that is equal to that v nu, so sorry, it is nu, okay, great. So we can write nu here, then partial of tau, right, plus x nu partial to x prime nu by partial x mu partial x k, and right here, okay, you can write it v of t, because that's partial x k by partial tau. So that basically gives us the velocity, yeah? Having rank k. Okay. Now, in that case, if you talk about that, or if you talk about first that coordinate, this transformation or that differential transform, this is differential coordinate. Huh? If you talk about both these transformations, now what I'm saying, जो हमारी second order derivative है, if this will be non-zero, right? So if this will be non-zero, it supposes our this transformation loss, coordinate transformation, right? Because so that means it poses a big problem in physics. So can we apply? So if you have any physics law, so can we apply these coordinate transform, this tensor calculus to those equations? So this is a big challenge because so we are saying that all these laws they should remain invariant if you go from one frame to another. So that means so there's a problem then because I'm saying that if our this second order derivative will be non-zero, so that means the rank. Suppose if we have some tensor of rank one, so your so this gives us some another tensor but of same rank, but the rank will change for this second order derivative, right? So that means so this basically we can say that this causes a serious problem for the physicists to apply this tensor calculus in some physics law, right? So now you can say that suppose if you talk about that as I already told you, so so I will give you some geometrical interpretation in that case, right? So why we are basically, so how we can get rid of this second order derivative, or what is the physical significance of this derivative? ये हमें क्या कहता है जो हमारी second order derivative है, right? So I will offer you some geometrical interpretation for that. Suppose if we talk about the motion of a particle along a trajectory, right? So for the मैंने आपको यहाँ पे suppose I talk about that we have some trajectory of a particle, right? So this is the trajectory of a particle made by the particle in position vector r of t, right? And what will be the velocity component? If you talk about the velocity component, so it will be tangent to that. So this will be your v of t. Okay. So this is very clear. Right? So from our fundamental physics class, so this is clear to us that the velocity component will be tangent to the trajectory that is traveled by a particle, and r of t is our position vector, right? So now what? So if you talk about now in Euclidean geometry, so in Euclidean geometry, so this RT and VT remains in the same plane, right? So if you talk about that in Euclidean geometry, so this R of T and VT, so they will lie in the same plane. So they will lie in the same plane, right? But if you talk about in some curved space, right? So in that Euclidean space, in the three-dimensional in Euclidean this plane, in Euclidean geometry, you can say that these lie in the same plane. But if you talk about in curved space, so this R and this T they doesn't lie in the same plane. So what does it tell us? So that means for two observers, the story is different, right? Suppose if you talk about that, if we have some sphere, and if you talk about the two-dimensional motion, or if you take now, if you have this, so if we have a sphere, right, and if you talk about that, this we have some two-dimensional sheet on this sphere, right? तो अगर अगर मैं आई एम बेसिकली ऑब्जर्विंग दिस आई हैव सम स्फीयर मेरे पास एक स्फीयर है तो मैं कह रहा हूँ कि आई एम बेसिकली ऑब्जर्विंग सम प्लेन टू डायमेंशनल शीट सो दैट फॉर मी इट सीम्स टू बी अ कर्व्स तो ये हमारा कर्व टू डायमेंशनल शीट है राइट तो मेरे लिए क्या होगा तो दिस विल बी कर्व्ड टू डायमेंशनल शीट राइट बट फॉर दोज or you can say that the inhabitants which are lying within the sphere तो आई एम सिटिंग हियर, तो ये मैं हूँ, दिस इज मी, राइट। तो मेरे लिए ये क्या होगा, जो शीट होगा, दिस विल बी, दिस टू डायमेंशनल शीट विल बी कर्व्ड वन, राइट। सो दैट मीन बिकॉज आई एम लाइंग इन द थ्री डायमेंशनल स्पेस, तो मैं खुद एक थ्री डायमेंशनल स्पेस में लाई करता हूँ, राइट। Okay, so that means I can visualize this sheet. तो मेरे लिए ये जो sheet होगा, this will be the curved sheet, right? But someone, if someone inhabitant which is lying on the sphere, तो sphere इसका part होगा, तो for this it will be some plane sheet. So what does this tell us? So there's a big difference between this. So that means it depends upon in which frame of reference you are saying. What's So either you are, because for me I am the outsider, तो मैं आउटसाइडर इसके लिए हूँ, तो मेरे लिए जो है ये कर्व्ड शीट होगा, टू डायमेंशनल प्लेन शीट। बट अगर कोई स्फीयर पे होगा तो उसके लिए दिस इज अ प्लेन शीट, सो दैट मीन्स वन डायमेंशन फॉर दिस पर्सन, फॉर पर्सन टू, दिस इज पर्सन नंबर वन। तो जो पर्सन टू है इसके लिए जो एक डायमेंशन दैट विल बी हिडन, right? Because so one dimension is hidden for this one, for this person, which is the inhabitant or which is the part of this sphere. इसके लिए प्लेन शीट दिखेगा, बट फॉर मी आई एम आउटसाइड, सो आई एम लाइक इन द थ्री डायमेंशनल स्पेस, बट ही इज लाइक इन द टू डायमेंशनल स्पेस, राइट। सो फॉर मी द ऑब्जर्वर वन, राइट, तो मेरे लिए एक कर्व्ड शीट दिखेगा, राइट। सो दैट मीन्स अगर so we can say that, so there is, अगर आपको फॉर एग्जांपल, और इफ यू टॉक अबाउट दैट, मैंने आपको ऑलरेडी कहा कि अगर हम देखेंगे फॉर एग्जांपल, आई एम सेइंग दैट this one, that velocity and that position vector, right? So I am saying that they lie in the same plane but in Euclidean geometry, right? In Euclidean geometry they lie in the same plane, but they don't lie in the same plane, right? So that means अगर मुझे देखना होगा, for me, so this velocity is tangent to the motion trajectory of the particle, right? Because to visualize this, to visualize that velocity is tangent to the trajectory of the particle, so I should be in some curved space, right? So मैं curved space में, then I can visualize that velocity is tangent to the particle, trajectory of the particle. But for that person, which is basically the inhabitant of that region on the sphere, तो उसके लिए, so this R and this V of t they lie in the same plane. So that means the concept of the derivative of that this position vector has no meaning for it. So for him it is that motion is local, right? For me it is non-local. So that means basically I am lying in the curved space-time. So that means, so what we have concluded. So I hope you are getting it. Maybe I can revise it maybe in some coming lecture. But what I will conclude here that, तो जो मेरी second order derivative है, second order term है, it is because of the curvature of space, right? So that means, so I need to take, so just check that. So this term is because of the curvature of space, right? So that's why I am getting that the transformation laws gets violated because of this term, which is due to the curvature of the space, right? So I will give some more example. Maybe in our coming lecture we will talk about one powerful example that's basically called the affine connection. So we'll talk about that and we'll see some interesting factors hopefully in our coming lecture. And thank you.